You know quite a few reactions related to the substitution chemistry of benzene, and also some reactions for interconverting functional groups already on a benzene ring. We have quite an array of synthesis problems that we should be able to approach. So in this particular synthesis problem, we're going to start with benzene, and through some series of steps, the number of question marks is not related to the number of steps that might be required. There might be multiple steps, but it's up to us to figure out how many steps it might take. We're going to try to convert benzene into this product. So here's the problem. Start with benzene. You can use any reagents that are necessary and to get to this type of structure here. So think about that a little bit, and then we'll come back and do an analysis of this problem. If we look at this product, maybe the first thing that we recognize is that the chlorine and the ethyl group are meta to each other on the six-membered ring, but that the chlorine is an orthopara-directing group, and the ethyl group is also an orthopara-directing group. So how do you synthesize a disubstituted benzene where two groups are meta to each other, but both of those groups are orthopara-directors? So think about that. Retrosynthetically, we might imagine that one of these groups came from a somewhat different group that was, in fact, meta-directing. So, for instance, we know that an alkyl group can come from the corresponding acyl group by reduction. So, retrosynthetically, we might imagine that this compound could have had as its precursor this one. And now we have two groups that are in a meta relationship to each other, but at least one of them, namely this acyl group, is a meta-director. So maybe we could generate that by chlorination of this compound. And then this compound could itself come from benzene. So a good way to approach these problems is in the retrosynthetic sense. Ask yourself, what might be an immediate precursor of this compound? Work your way backwards to the original starting material, but that's really only part of the problem, maybe the harder part of the problem. But it's only part of the problem because now we have to provide the exact reagents and conditions to go along the forward direction if we were going to implement this synthesis in the lab. So pause the video and go ahead and see if you can provide the reagents to go along this pathway. So the first reaction here is a Friedel-Crafts acylation reaction. And so for that, we're going to need the appropriate acyl chloride. And then we use aluminum trichloride to promote the Friedel-Crafts acylation. So that's what that reaction is. How about this one here? We now have a meta-directing group on the ring. So to go from here over to here, what would we do? Chlorination, and to do that we need a Lewis acid, so we could use ferric chloride for that. And then finally, this transformation here, we need to do a reduction. It turns out that aryl chlorides might be susceptible to reduction themselves under Clemmensen reduction conditions. So in this particular case, it would probably be better to use a Wolff-Kishner reduction than a Clemmensen reduction. If you ended up using the Clemmensen reduction, it wouldn't be the end of the world. It's the right idea. So remember, Wolff-Kishner is a complement to the Clemmensen reduction. It's done under basic conditions instead of acidic conditions. And so these are the reaction conditions and reagents for achieving reduction of the carbonyl group all the way to the CH2 group that's here in the product. So strategically, the key to this was recognizing that in order to have these two groups be meta to each other, there must have been at some point in the synthesis a meta-directing group on the ring that we then were able to convert into the desired alkyl.